Hello everyone. Today I'd like to talk about the last data structure in 174, which is an incredibly versatile and ubiquitous data structure in computer science known as the binary tree. It's a strict generalization of a linked list, so it's a linked list with a little bit more structure. Let's examine what it is. So it's a tree where you can branch in two places at every branch point. Now, in computer science, we tend to draw the trees from top down instead of bottom up, like we would normally see a tree branching out. This is because we don't know how big the tree is actually going to be, so it makes sense for us to draw the beginning of the tree at the top, and then we'll draw it branching out in this direction. So you can think of it a little more like the root system. So a tree consists of a bunch of nodes. Like in a linked list, a node is a container object. Let's suppose in this discussion that the nodes are just containing ints. So I'll start the first one off as containing the number 10. Okay, now so far you could think, well, this maybe is going to be a linked list. So maybe 10 gets linked to, let me say 10 gets linked to 7 over here. Okay, so far it looks like a linked list, and then maybe 7 gets linked to 3 over here. Alright, so I've got a node, I've got a reference to another node, and then a reference to another node. But here's what makes it different. As I said, you can actually branch. So 10 can have another arrow, can have up to 2 non-null children, is what we call them now. We don't just call them next, we call them children, because we're thinking of this in a hierarchy. So let's say that 10 over here has a child with the value 15 in it. So what we say in this tree, 10 is the root. We call that the root. 7 is the left child. And 15 is the right child. And so what we say is, back in the linked list, we had an arrow which we called next. These arrows we're going to call left and right, respectively. So here's the left arrow, here's the right arrow. And every node has a left and a right arrow. Sometimes they'll be null, like on this one doesn't have any child on the right. It does have a child on the left. This one, they're actually both null here. But actually, let me make it a little more interesting. I will add a couple children here. So I'll say maybe the left child here is 12, and the right child is 20. Let's say that. So the node that has 15 here has its own left child and right child. And so you can keep going and branching out as much as you want. Okay, so it's kind of like a linked list. It has these paths within it that each are individually linked lists. So like 10, 7, 3, you could think of as a linked list. But it has a bunch of them. So 10, 15, 12 is also a path. 10, 15, 20 is also a path through this thing. So it has more structure. It can hold a linked list, right? If all the right children are null, I could have a tree that looks like this. I won't even put values in, I just want to show you the topology of it, how it's connected. So, if every node could have a left child, but no right children, in that case, I can represent a linked list with a tree. So what you see is, a mathematician would say a tree is strictly more general than a linked list, because I can represent any linked list as a tree, but there's more structure here, so I can represent other things. So even though I'm not making use of the right children in this tree, I can have other trees which do have right children. And this certainly I could not represent as a linked list. Okay. So I just wanted to point that out here. Here's an example of a linked list implemented as a tree. Okay. But usually we're going to branch out. All right, so let's see. A couple other definitions. So I told you that the beginning of a tree is called a root, just like the beginning of a linked list was called a head. Every node has a left child and a right child. So the root is a special node, that's where we start, but every node has a left child and a right child. We call the node that came before this one the parent. So 7's parent is 10. Actually, 15 also has a parent of 10. And you could imagine, there is an implementation of this where I actually keep track of the parents. That's sort of the analog of a doubly linked list. So I may also decide to have an arrow back to the parent. For now, I'm going to keep it simple, like a singly linked list, where I just have an arrow to the children, not to the parent. Okay, so we got parent. And the other thing is, a tree is really a naturally recursive data structure because this is itself a tree. So this here is a tree. Oops, I accidentally selected the other thing. This is a tree. It's got a root, which is 15. It's got 2 children, a left and a right. So we call this a subtree here. So the right child of a particular node is a node, but that node itself may have a whole bunch more nodes. So it's a tree in its own right. We call it a subtree of the larger tree. So I'll call this a subtree. And so a tree is made up of trees. This is a recursive way of thinking about it. So I could actually take this entire tree, make a copy of it, and put it down here. Let's say maybe this is, we'll make this a left child here. Okay, so now this is a tree. The root is 10, and see I can go path 10, 15, 20, 10, 15, 12. So this is interesting. I can quickly construct very large trees by making copies and just splicing them in. Okay. So I just wanted to explain that recursive notion of a tree. But let me clean this up a little bit and go back to just the simpler one here. Okay, so this one branches out in 2 directions in the beginning. This one only has a left child, no right child. This one has both a left child and a right child, and then it stops. And you can keep going, as I said. So let's see how we can translate this into code. So it's going to be a lot like a linked list, actually. Let me have this picture to the left as I code up things here. So we're going to have a data structure called tree node, which stores the value that we're containing as well as the arrows that we need to keep track of. So let me make everything public just to be easy for now, so I don't have to have all the getters and setters. So what I'll say is, first I need the value that's stored at this node. I also need a reference, so a pointer, to the left child. And then I also need a pointer to the right child. So this is what makes it a little different. And you could have a pointer to the parent, the one above it, but I'm going to neglect that for now. Let's just keep it simple. All right, so when we go to construct this thing, just like with the linked list, let's say we pass along a value. So we'll remember what that value is in this node. But we'll set the children to be null by default. So nothing there to begin with. Maybe we'll add something later. Okay, and then for the binary tree, actually it's going to start off very simple. Just like a linked list, we need a place to start, and as I told you here, we call it the root. This is the top of the tree. So I will say tree node root. And when I construct this, I guess I will just say oops, I'm still in here, so I'm not gonna do the header file thing. I'm just gonna write binary tree. I'll just say root equals null. Okay. So let me try to make this tree. I'm not going to create methods yet that actually add things. We're going to build to that as we go on this week. Let me actually just manually set up all the nodes for this tree here. So I'll just make a method. I'll call it example tree. So what I'll say is tree t. So that's going to make a new tree with a null root. And let me make a bunch of nodes here. So in this example, I have 6 nodes. So I'll say tree node 10, tree node 7, tree node 3. So I'm just passing to the constructor the values that each of these nodes hold. Tree node 15. Oops, need my capitals there. Tree node 15, tree node 12, and tree node 20. Okay, so the root is 10, right? So I'll say t.root is, these are object references, so I'll say the address of that. Okay. 10 has 2 children. So I say 10 dot left equals 7, right? 10 dot right equals 15. Okay, so I'm good with that so far. Then I say 7 dot left equals 3. We can leave the right be because that should still be null. There's no child of 7. Now I say 15 dot left equals 12. 15 dot right equals 20. And that's it. Okay. So then I can say things like, all right, well, what's the right child of the left child of 10 of the root? So I could say something like printf root dot left. So that's a reference. Then I have to say arrow notation. Oh, let me do what I said a moment ago. So I'll say the right child of 10. So root dot right. And right arrow. Let me do the left child of that. And then I'll print out the value. So root dot right. And then that's a reference, so I have to use arrow notation. Left. And then the value at that node. So let me just show you. Here's all the code. So let's see what that prints out. It should print out 12, right? So I go right, then I go left, I print the value. Let's just compile that real quick. And we have an error because root is actually in the tree. Okay, this will actually make it a little clearer too. So I have to say tree t.root and then arrow right because root is a reference. So let me just update that. Okay, so we have to go, we're going to the root of the tree, then we're going right, then we're going left, and we're printing out the value. So let's try to compile that now. And I didn't call it tree, it's called binary tree. Okay. So just trying to get all my stuff ironed out here. Okay, so let's see that this should give us a 12 like we said. And I need to call the method too. Okay, I'm making a lot of mistakes this morning. That's okay. So I had my main that was empty, it didn't do anything, but I need to call this method. Okay, so it says it's 12. Let me put a line break so we can see that a little more clearly. Okay, so just as I said. So when you deal with these data structures, you're doing a lot of arrow following, arrow chasing, pointer chasing. So you just go through right, root, then right, then left, and there I am. If I keep going, let's say I try to go left again. There's nothing there. So it may give a segmentation fault. Let's see if that happens. So I'm trying to say go to the left of 12 and then tell me what's there. Probably going to give a segmentation fault, right? Okay, so you should be aware that these things can be null. All right, so I'm just going to have you do a quick little exercise, making sure that you understood this data structure.